Okay, so as I mentioned, my name is Shabtai Isaac. I'm from Ben-Gurion University of the Negev in Israel. What does real-time project control really mean? Well, first of all, real-time project control is very important. It's necessary, since in most construction projects, we have significant deviations from the originally planned goals, whether it's the budget, or the schedule, or quality specifications, or required safety measures. And the disadvantages of manual project monitoring have been well documented. Construction managers simply cannot be everywhere at the same time. And they also find it challenging to process all the information in real time. So the end result is that very often we don't really know what is happening in a construction project in real time. Now, luckily, we have, what's happened? Got stuck. Oh. Slow, sorry. Luckily, we have quite a large number of automated data collection technologies available now, ranging from RFID to cameras and image processing software and tags with which we can track assets on the site. And research into their application for construction project control has been going on for quite a number of years. However, the actual application of such technologies in construction projects has so far been very limited. And we have to ask ourselves why, because there is an obvious need. We have solutions, but they haven't been applied, not at a wide scale. So I would like to propose that this is due to something called the substitution myth. It's not a term I invented. It's a well-known phenomena in other domains, such as air traffic control, for example. And what it says is that you cannot just simply substitute a human action with an automated action without this having a large impact on the system. If you assume this, often you will not, this technology, this automation will not meet your expectations. And this is for a number of possible reasons. First of all, frequent changes in plans are a problem. If we automatically monitor something, we usually compare what is happening with what was originally planned. When there are frequent changes in the plan, as is happening in most construction projects, this is a challenge, and it's not a trivial one, how to deal with this. How the automated system should communicate with human operators is a big question. When should they be provided with alerts? We've just seen the example of the Boeing 737 MAX, but it also happens in many other domains. And this leads us to the problem of data overload. It's very easy to collect lots and lots of data with automated systems, but then it's a real challenge for human operators to process all this data. They get quickly overloaded, so we have to deal with that as well. I always like to show this chart. This is actually the original chart that was developed by Mr. Gantt. And if you look closely, you see that it wasn't used, he didn't use it for planning schedules. He actually used it for monitoring, for tracking the performance of machines at a very high rate, almost an hourly rate. And in his book, in which he published this chart, he was actually very critical of plans and schedules, which he said look nice on paper, but aren't applied in practice. So I think it's ironic that nowadays we use this Gantt chart exactly for that purpose. So monitoring is important. We shouldn't just plan, we should also carefully monitor what is actually happening. And we have to, of course, understand that monitoring takes place in a quite complex process. Of course, we transform the design into an execution plan, first of all, through the product-to-process transformation. Then we can start monitoring what is actually happening on site. And then we can compare what we have monitored with what was originally planned. We can update the plan according to the as-built actual situation. And if we find significant deviations, we can take control measures. We cannot automatically take them. We have to, first of all, analyze the impact of possible control actions on the entire project. Again, by analyzing this using the plan. And if the impact of those control measures is as desired, we can actually implement them and update the plan accordingly. So we see that monitoring takes place in a very complex process, actually composed of a number of sub-processes, all of which are interdependent. So when we want to automate monitoring, we really need to consider all those other processes. If we just substitute manual monitoring with automated monitoring without considering all the other processes, this will probably be ineffective. We have to adjust also the planning and the control processes and integrate them all with the automated monitoring process. We have to take into account data granularity. When we plan activities nowadays, we don't take into account individual components, but with automated monitoring, we usually do. We have to take into account different time scales. We usually plan activities according to a time scale of days or even weeks. But in monitoring, we can do it at the scale of minutes or even seconds. So we have to somehow synchronize this in order to define what we really mean by real time. So I would like to, first of all, pose a number of questions that we need to ask ourselves before we decide how do we do automated monitoring. What information do we actually need for the control purposes is the first question. Second question is, what kind of data can we collect with our automated technologies? Right, there's some delay, yeah. Third question is, how can we actually process this data in real time in order to provide us with the information that we need? And how should we revise accordingly, not just the monitoring process, but also project planning and project control? And the approach I would like to propose here, which I try to apply in different domains, is, first of all, decomposing the project into certain segments, which should preferably be minimally interdependent. So I try to divide a project into certain segments which can be easily controlled. Then we need to define certain control points at the interfaces of those segments, because when something goes wrong, when there's a certain deviation in a specific segment, we want to prevent this deviation from spreading, from having an impact on the entire project. That is the approach. And then we can carefully monitor the status of those specific control points, which are of interest to us. And, of course, provide alerts when there are significant deviations at those control points. So that's the approach. Of course, following that, we can update our planning and control actions. I would like to give you a brief example of an application of this approach. Actually, two examples in two domains. One is schedule control, and the other is safety control. So in scheduling, we usually present our schedules using these Gantt charts, which I showed earlier, but we actually plan our schedules still using the critical path method, a method which hasn't changed for almost 60 years now. And in the critical path method, we usually assume constant production rates for each activity. We define activities according to their endpoints, the start and the finish of each activity. And we define relationships between activities only at those endpoints: finish, start, 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 finish, finish relationships, and so forth. So what that means is that basically, critical path method ignores everything that happens during the execution of an activity. Any mid-activity deviations are not relevant. We can collect data on them. We have no use for them in scheduling. We cannot formally incorporate such data into our schedule. And this is, of course, a big problem. Automated monitoring won't help if our schedule is planned according to the traditional critical path method. So what can we do? Well, okay, so this is the current situation. We plan an activity according to a certain ideal constant production rate. Well, we know that in practice, the production rate will differ, and we can actually know in advance already how it could differ. We might have a learning curve, we have different conditions during the execution of the activity. And of course, we could then have a situation in which the activity in practice will take longer, but simply replacing our originally planned activity with the longer one, which also has a constant duration, production rate, will be a mistake. It won't solve our problem because in such a case, if we have a successor activity, this might still cause certain problems regarding, for example, mid-activity collisions. So we have are two activities related to each other with endpoint relationships, but any mid-activity collision will be simply ignored in critical path method. So how can we solve this? Well, what we can start to do is divide our activity into certain segments. And we can define control points at the beginning and end of each segment. For example, each segment will have a different production rate. Or even if they have the same rate, we can define certain control points at certain intervals. And then we can do that also for successor activities and connect all the control points through point-to-point relationships, which are mid-activity relationships. And I won't go into technicalities because I don't have the time, but I would like to stress that this is not the same as simply dividing up an activity into lots of smaller activities. Because if you have a project with hundreds or thousands of activities, that would mean having a schedule with tens of thousands or hundreds of thousands of activities. That's not manageable. But this is manageable. And using such relationships and such control points, we can carefully track the status of activities at the control points and then update our schedule using those point-to-point relationships. Another example, safety control. So there has been a lot of research on safety control and how we can improve it using automated tracking of assets on site, equipment or manpower, in order to prevent, for example, workers from entering high-risk areas, which we have defined and identified in advance. 3 minutes, oh my God, okay. And we do that using virtual fencing. So we have certain alerts whenever a worker enters a high-risk area. But usually these alerts are provided either too late, when the worker is already in that area, or if we're more conservative and we enlarge the high-risk areas, the virtual fencing, they will be provided too often, then those alerts will simply be ignored. So what can we do? Well, with automated data collection technology, we can support proactive alerts. Now we'll run through this because it's taking too long. But what we did was we developed a probabilistic model with which you could actually identify when the safety risk exposure of a worker is excessive in terms of space and time, whether he's moving too close to a high-risk area or he's staying too long in a certain location where there are safety risks, not just deterministic alerts when he's already in an unsafe area. We applied it using Wi-Fi technology, which is cheap but relatively inaccurate. So we had here an accuracy of plus minus 2 meters, which is not a lot, but we managed to compensate for that. As I said, using a probabilistic model in which we didn't have just high-risk areas for which we provided a deterministic alert whenever a worker enters them, but also medium-risk areas. We could actually track the location of the worker in this medium-risk area. And using certain, I'm sorry, I'll run through this, okay, because I'm out of time, right? We could define for each such an area certain probabilities. The lower the risk, the higher the probability that a worker will be located in such an area. In a high-risk area, you want a very low probability. And then we define certain probabilistic decision rules with which you could automatically identify, for example, such an upward trend, which means a worker is getting closer and closer to a high-risk area. We want to provide an alert, even before he enters it. For example, if there's an unprotected ledge and he can fall off it. Or we could provide an alert and just look at those data points, ignore all the others, when a worker is for too long a time in a medium risk area. For example, there's noise there and he's not protected. So, to conclude, the proposed approach is to adjust planning and control processes in addition to the monitoring processes in order to support automated data collection. And I try to do this by decomposing the project into controllable segments, okay? According to each domain, of course, and define certain control points at the interfaces of those segments, which we then carefully track. And we warn whenever there's a significant deviation at those control points. And I've done it in other domains as well. Here's an example, work packaging. How do you divide the project into work packages that are relatively independent and control their interfaces? Or waste control. How do you identify specific actions in each activity which are causing the waste and then controlling them, tracking the inflow and outflow of material in those actions. That's it. Thank you very much.